Okay, Max Planck. Max Planck is our grandfather of the quantum theory. He's noted with the black body radiation theory. And just a side note here, he did talk Heisenberg into staying in Germany. The black body radiation is this concept that if you have a black body and you heat it up, you see it glowing a red color. Underneath the classical model, that intensity should continue to grow. It's an exponential relationship. Since you and I can be in the lab using the wire gauze, heating it up with a Bunsen burner, and the fact that we walk away alive is evidence that that is not true. So Planck figured out that there must be some kind of mathematical relationship to explain why we see red when a black body glows. And so his relationship was E equals HF. H is his constant, 6.63 times 10 to negative 34 joules times seconds. And that basically brought that curve back down. And that rainbow that you see on this graph is a visible spectrum. And so for the right intensity, right wavelength, we'll get a red color on our wire gauze as it heats up with the Bunsen burner. So the things about this, the classical model is what we started with Rutherford and with Chadwick and with Thomson. The classical model with the nucleus in the center, and you have the rings, and you have electrons, and this whole point is that all this work that these guys are working on, it is not coinciding with their classical theory. There's something else going on. And so the quantum theory that Max Planck proposed was that you had these packets of energy. Okay? You had these packets of energy that are being absorbed or emitted. Back into Bunsen and Kirchhoff. Bunsen and Kirchhoff brought us the spectroscope. And on the spectroscope, they talked about absorption and emission lines. This is what we're talking about. The reason we don't get a continuous spectrum when we burn our metal salts, the reason we get those fingerprints has to do with the electrons jumping from one energy level to another, or jumping down, being absorbed or being emitted. We will talk more about the quantum theory. Enrico Fermi worked in Rome, and he did work with bombarding nuclei with neutrons. He worked through the entire periodic table looking for trends. Then that's the reason we like to mark him right here, is because of his work with the periodic table. They did fire in 1934 neutrons at uranium, and he created what's called a transuranic, which just basically means you're past uranium on the periodic table. Hans and Meitner and Friss, they all continue to work on the experiment. We also credit him with the first nuclear reactors called the Chicago Pile 1. He worked and excelled in both theoretical and experimental physics. He demonstrated the very first nuclear chain reaction. He had several patents for the use of nuclear power and received a Nobel Prize in 1938. And that would lead to the quantum theory. I'm sorry. His work leads to the quantum theory in support of it. And he also used Wolfgang Pauli's exclusion principle, applied it, and that will also support the quantum theory model. And we'll talk about that soon. This is the Chicago Pile 1 first nuclear reactor, just so that you have a scope of what we're talking about. So what is uranium-235? So uranium-238, I talked about, is more abundant than U-235, which is why when you look on the periodic table, uranium's atomic mass unit is 238. Okay? There are certain things we have to have happen in order to control a nuclear reaction. And one of the things is you have to have what's called a moderator. And a moderator is going to control how fast or how slow your reaction goes. And two moderators that we can use are graphite and heavy water. Okay. Nuclear equations. So I talked earlier about alpha, beta, and gamma decay, and I didn't write them out. But this is them written out in equation form. So if I have an alpha decay of uranium-235, Then I take my uranium-235 atom and it decays into alpha, 4,2 helium. The other isotope that's given off is thorium-231 over 90. That 231 plus 4 equals 235, and 90 plus 2 equals 92. Your left side must equal your right side. With beta decay, I get a -1 electron being emitted. And so we talked about earlier about Hahn and that he did his experiment. Specifically, we talked about 239. U-239 was being used. But for this example, we're using U-235. That electron actually changes into a proton on emission, and so you get a 93 being produced, which is Neptunian. Again, notice that the 235 plus 0 equals 235, and 93 plus -1 is 92. In a gamma decay, we write 0, 0 in a gamma sign, and we get uranium on both sides. It's a high energy. Referring to the fast and slow neutron, fast neutrons pass through the uranium nucleus without causing it to split. That is a problem. We talked about whether or not it would be absorbed or emitted. A slow neutron, if a slow neutron is done right, they can be absorbed. The key thing we're looking for is we're looking for the protons and neutrons to be unbalanced. Elements whose neutrons and protons are balanced between each two do not undergo nuclear decay generally. It is when you have too much neutrons compared to your protons, when that becomes unbalanced, those will undergo nuclear decay. That's what we're looking for. And it goes back to what Bohr talked about, that Bohr mentioned that there was there had to be something that holding that nucleus together. And there's arguments being made, especially by Chadwick, that the neutron is what's responsible for holding that nucleus together. Okay? So again, we're looking for the neutron and proton differences to be asymmetrical, I guess is a way of saying it. Okay? We've discussed both of them. I've talked about a chain reaction. There has to be a material that will allow this to happen. It's called a moderator. So we can either do heavy water, which is deuterium isotopes, and that means that instead of being hydrogen being 1, 0, which means 1 proton, 0 neutrons, it means I start adding some neutrons there. Graphite also works for that too. A few things on here I want to note. The reason for slowing it down, neutrons, you want them to have a certain threshold as they're hitting the atom, okay? Because if you have the wrong one, it can be absorbed. I've also mentioned that U-235 is very rare, which is a problem. Two scientists closest in Dickel from Germany had a process that was in the process of separating U-238 and 235 based on their gaseous forms of isotopes and exposed to different temperatures. The problem is that when you're forming uranium into a gaseous compound, you're working with a very unpleasant substance that corrodes basically on contact. So that was a problem that they had. This is what some of the earlier nuclear reactors look like. The substance hanging from there is what we would call, that's your kind of like your control rods, and it goes into a water bath to control it. Deuterium, I talked about this earlier, this is a hydrogen isotope. So hydrogen has two isotopes, deuterium and tritium, which refers to the count of the nucleus. And so deuterium is a byproduct of some industrial processes. And again, it's a better moderator than graphite because graphite must be completely pure. So the next one is a map. This map is of the nuclear sites in America, and the reason I put it here is we're getting in the mix of what's going on of the Manhattan Project. And the one thing I want you to notice is we had multiple sites across the United States working on this project. Oak Ridge and Los Alamos are two of the main areas that we're working on this. Los Alamos is where we're going to develop it. Oak Ridge was developing the plutonium to be used in Los Alamos experiment. Leo Szilard, he headed work with Fermi and was determined to help someone else beat Germany for the atomic weapon. He truly feared that which Hitler had talked about. He talked other scientists into moving in America to help out with this. And he did talk Roosevelt into writing a letter. Some things about him that are important to note. He is the one who really worked and developed a good idea on the nuclear reactor. He also is credited with testing on large-scale uranium oxide and graphite and determining that heavy water was the best one to use for that. And this is kind of like his setup for what the reactor would look like. It's one of your first models of a reactor. This is ours design.